Here at the University of Texas at Austin, students within the Drilling Rig Automation Group are working to develop a new generation of autonomous drilling rig technology. One team is developing NanoRig, an entry into the DSAT's drilling rig competition, a competition to design a machine capable of autonomously drilling a vertical hole in a block of concrete, which may include inclusions to complicate the drilling process. The machine itself is limited in power, size, and cost, and entries will be judged on cost, drilling speed, efficiency, and ingenuity. Most simply, a rig requires two actuation systems, one to provide axial motion to the drill string and impart weight on bit, the other to provide rotation and rotary cutting force to the bit. Axial actuation may be accomplished in a variety of methods, including a pneumatic or hydraulic system to drive a series of pistons, a drawworks-driven lift system with the possible mechanical advantage of a pulley system, or a rack and pinion or mechanical screw that can provide precise motion and force. Weight on bit may be active, provided by the axial actuation, or passive, provided by the weight of the traveling components. Rotational actuation may be accomplished using either a top drive system or a Kelly bushing. A Kelly allows for a stationary motor, while a top drive allows the motor to be used as a part of the passive weight on bit system. Structurally, a rig may be freestanding, requiring a large and potentially heavy superstructure, or being integral with a concrete block and thereby using the weight and size of the traveling block for stability.
So what we're trying to achieve is to provide the fast ROP, but in the meantime use the smart control system to avoid any stuck pipe or vibration problem.
Desiring to reduce weight and size and to improve mobility, the team chose a sample-mounted design that uses the mass and size of the concrete block as an integral part of the structure. A series of outriggers act to clamp the rig onto the block and provide additional stability. A continuous drawworks system, in the form of a belt drive, provides precise axial position and force and is driven by a stepper motor. For mechanical simplicity, a top drive system with a 1.5 kilowatt AC motor is directly connected to the drill string. To reduce the power requirements of the drawworks, to provide maximum power to the top drive, a passive weight on bit system is implemented that utilizes the weight of the top drive motor and uses the drawworks as a brake. The top drive AC motor is controlled using a variable frequency drive, which eliminates the need for speed and torque sensors due to the accuracy of current integration within the VFD. The stepper motor is driven by a stepper drive with a high fidelity encoder and torque sensor, allowing for precise measurement of top drive height and weight on bit. A high-frequency triaxial accelerometer is placed at the end of the drive shaft and provides vibration measurements to sense drilling dysfunction. Many components in the rig design are dual-purpose. The outriggers both secure the rig to the sample and provide additional stability. The top drive motor acts as a rotary actuator while providing weight on bit. The VFD both controls the top drive as well as provides the necessary sensory output, and the concrete block acts both as a sample and as a stabilizing structure.
Our goal is to predict what kind of different regimes we're going to get in the cement block and try to plan accordingly. So once we detect we hit a different regime, we change our controller or our mode accordingly and manage with the situation. That's our primary goal in the controls.
NanoRig is a compact, lightweight entry into the DSAT's competition that maximizes the available rotary power, features many dual-use components, and allows much of the focus to be on effective control strategies. It is also easily extensible due to its small size and accessible tower.